Yay. So while we're waiting for more people to show up, Ivett, I'm gonna ask you a few questions that are missable. Are you there?
Give me a sec. Okay, here.
So one thing I'm dying to know is in your talk, will you be able to help us get far enough to be able to predict that, oh, LLM, this LLM or all LLMs are, the current generation is likely to not be able to do X, right? Like being able to know, oh yeah, it seems very similar to things it can do, but it won't be able to do this, and here's why. Right? The more, because if I know what workarounds I need to create, because
Yeah, so obviously, like the goal of the talk is to make sure that you have a basic understanding and an intuition on what is happening in the background. I don't promise you will have definite answers. Probably no one has. Uh, but you will have a more clue about these things, yes. I'm not saying that you will know everything.
right, but even occasionally being better um at understanding what the limits are. Because I think at times I am
Yeah,
um
you will get a better understanding of the limits. Yeah, that's
let
for
me
sure.
let me also, okay, by the way, we're trying to kill a few minutes here while we're waiting for people to show up. So um ask questions that are not too good, that are okay if people miss them. Um
I wasn't in
Llewellyn,
one.
do you have anything
What's your
to say
favorite
or share?
color?
Pink.
As it's changing in the room color when it's cycling through.
Yeah. Just a sec. All right. Happy to see you as well, Llewellyn.
Oh, and so that the algorithm, the Google, the YouTube algorithm doesn't misunderstand, feel free to stream this on some tab, some muted tab, so that YouTube will know that people care about this, which of course I don't think it shares information with Zoom, so it wouldn't know how many of us are here. By the way, it just came across, I think I probably only have Pro, so more than whatever it is, 13 people. So if anyone ever gets bounced out, let me know, or can't get in. I'll just upgrade to the one that gives us up to 200 or something.
In the meantime,
No
I
more
will
bucks.
try to share my screen just to make sure that it's working. Yep. Okay. You see my screen, correct?
What screen do you mean? Yes, we can totally see your screen.
Yeah, the slide that I have up there.
Demystifying generative AI.
Yep.
Oh, I like the little arrow. Little
Yeah, I just wanted to make sure that because I run on two screens now, One screen is what you see, and the other screen is my notes, so that I know what I'm going to talk about in every step.
Yeah, it could be really annoying if you were displaying, your confidential client data or something.
I actually have, I'm not sure how long we want to wait. But while we're reading, maybe I will just ask the first question that I have on my slides, because this is something where I want to discuss anyway. So I would encourage people to come a bit on screen if you can, if you are comfortable with being streamed. And I just want to ask this question. I am curious what guesses you would have about how many lines of code you need to implement a large language model like Llama 3, which is Facebook's. And if you know the correct answer, please don't spoil it for everyone else. For those of you who don't know the correct answer, I would be really curious what your guesses are.
Well, why don't you stop sharing your screen so everybody's face can show up then?
Yeah, okay. Anyone? Any guesses about how many lines of code does it take to implement a large language model like Llama 3?
Now you're talking about all the technology that does all the learning, not any of the data, but all of the
I'm,
technology that would do all
I'm
No, not the learning, the one that does the actual,
yeah, the prediction, like
the prediction.
the thing that you download and run
Yeah.
without the data, just the pure code.
Okay, so I think I know the answer to that, so I won't answer unless
Yeah, I think I know the answer to that too.
Okay. Anyone else? We don't have too many people in the room, so you can also write it in the chat, by the way, if you feel comfortable writing in the chat. 300 lines, okay, that's one guess. Any other guesses from the other people here in the room? By the way, I know Arpad, and I know that his guess is way too well informed. All right. Well, I
you
guess I'm
include
gonna tell
all the
you.
design of the internals of a GPU. No.
Yeah, I mean, it depends, right? Because you could say that like the entire library that it is built on could, if you add that to it, maybe that's more. But yeah. But the large language model specific part of the code that is not reused across multiple things. Okay, so no more guesses. All right. Should we get started? What do you think, Eric?
Yes, I think this is a good time to start.
Okay, then should I just dive into? Okay. All right. Then welcome everyone, and let me just reshare my screen again. So that I have it up here. And then once I find, yep, okay. Right, so that was the slide that we had. And I waited a bit for any guesses. For now, the only one that we got is 300. It's fairly close. The part of the code that is actually doing the prediction, that's about 500 lines. And the part of the code that is doing the training is also about 500 lines. So, and that's not counting the libraries that it is using in the background. But the message is that the LLM specific part of the code is actually not that big. And that's kind of perplexing. Like there is a lot of thought that went into this. How come that we have so little code to actually make that happen? And to follow up that, like there is this quote from Arthur C. Clarke that I really like, which is any sufficiently advanced technology is indistinguishable from magic. And
Boy, if I never really experienced this before LLMs. I certainly experience it with LLMs, boy.
yeah,
That really feels like magic.
and that's kind of my assumption that your starting point right now is this, that you saw all these AI technologies show up, and for you it's mostly just input, magic, output. Okay, and I have a plan because I want to change your perception from this through multiple steps to something else. And here's the plan that I have. First, I want to take this and I want to show you one speck of magic dust that is making this whole thing work. After we understand the magic dust that the whole AI thing is made of, then I would like to break down that big magic into smaller magics. Like what are the steps that are going into this? And then for each of those kinds of magics, I want to show you an intuitive understanding of what that is and what is happening in the background with those. And here's the disclaimer. I know enough to be dangerous around these models, but I'm not an expert. I used to be an expert. I used to work in machine learning. I have lots of friends who work in this field, and I talk a lot to them. So I probably have a better understanding than most people, but I'm not an expert. And the second disclaimer is that this is going to be a fire hose of information, and you're likely going to feel like this dog trying to just get part of the information, and that's fine. My goal today is not to make you an expert. I'm not an expert as well. My goal here is to give you enough context so that you know what you should be looking for when you get interested about certain parts of this whole big topic. And what I'm going to talk about, like if I wanted to go into detail for all of those things that I'm going to mention, that would be a whole semester worth of university course. Okay, so that's enough of the disclaimers, and then let's get started, and let's first talk about the magic dust. And like some of you might know this part, this is just neural networks. If you learned about neural networks before, this is going to be just a refresher. But the interesting thing is this, when I was working in, like, I was doing my PhD partially about machine learning. It was bioinformatics, but like the part of the thing that I was doing was machine learning. And in those days, we were very convinced that neural networks were a really good idea that just went nowhere. Like everyone was convinced that this is something that doesn't really pan out the way we expected. And then in 2011, something really interesting happens. What happens is that there is this competition for image recognition. And what happened was up until 2011, everybody was like, no one was working with deep learning or AI or neural networks or anything like that. Everyone was doing this traditional computer vision stuff. And then in 2012, there was just one model that was using neural networks, and it completely blew everyone out of the water. And the next year, everyone was doing neural networks. And that shift in 2011-12, that was something quite unexpected. And like only a few tiny things contributed to that changing. But we will talk about that later, like the most important idea that came in 2012. But before we do that, I just want to show you one very simple example of machine learning. Okay, so, and this is driving towards neural networks. So imagine this data set, and imagine that we know that this is actually coming from a linear, like something like a simple linear relationship, and we just don't know what are the correct parameters for it. So we just want to draw a line. And the simplest thing you could do would be to just draw a line from the first data point to the last one. Unfortunately, it's not really good. So the way machine learning people do this is that we define distance, like the distance of each measured data point to the approximation line. And then what we do is we take the function when you have a linear relationship, then you have basically two constants you can change, and then we create a function that is basically depending on what line we drew, how much is the error, and if we just plotted this, it's really easy to find that lowest point on this chart, and that gives us the correct line. So that would be how you do so-called linear regression. This is the simplest machine learning you can imagine, right? And it just says, find me the line that has the least error compared to the data. Now, we could do something smarter because like this one, I don't want to approximate this with a line, right? There is a better function for that. What function would you guess? What would you try to use if you saw data like this? This is not a rhetorical question, or okay. So of course, like a sine or a cosine would make sense here, and you could do the same thing, except like the error function would be a lot more complicated, but you would still be able to find a low value on this chart, and then like here somewhere, and then that gives you a good approximation. But of course, it's like a lot of pain to guess what function is right. You want something more general, and that more general thing is basically what we call like these artificial neurons or neural networks. And like, I'm not going to do the traditional intuitive or traditional way of explaining it, because I think that's easier to think of it as slightly differently, although it might not be as clear why we call them neurons. But basically what we do is we take the input as a vector, we multiply it with a matrix. And basically this matrix is the thing that we are going to look for. Now that just creates a simple linear function, like the line that we had, right? That's matrix multiplication is basically the equivalent of a line in higher dimensions. But then we want to introduce nonlinearity, because you can only do so much with linear functions. And the way we are going to do that is we are just going to remove all the negative values. We are going to truncate it to 0. And then repeat that a couple of times. So basically just do a bunch of matrix multiplications, and then if less than 0 equals 0. And then what we do is we look at this big function, and we just try to find the matrices that minimize the error for this function, given the inputs and outputs that we collected from some source. And that's it. Like, this sounds deceptively simple, right? And then the question is, why matrices? And the answer is, of course, because these things, the GPUs, are really good at multiplying matrices with each other really fast. And that's the only reason why we or mostly that, like that's the most important reason for us to rely on that. But what I want you to take away from this is that we just guess a function that has a bunch of like it has some structure that is very convenient for the GPU, but it's a function that has a lot of unknowns. And what we are going to do is we are going to try to guess those unknowns based on some algorithms so that it matches the data that we are training it on. So where is the magic? And here's the thing, like the reason this isn't that simple, because when you first come across this, it feels like the ultimate solution for everything, because now we just have to collect data and they are going to throw these machine learning algorithms at it and everything will be solved and everything will be beautiful. Problem is this, you need data and good quality data and lots of it. Because if your data is not good, then your results are, of course, going to have those errors in it. So creating a lot of data manually, that's a lot of work. Second thing is finding the right function and finding the minimum for the right function, like the error minimum for the function. So why is the function important? Like, why don't we just throw as many matrices into the mix as we can and as big as we can? The reason we don't do that is because there are two problems that you can come across. One is called overfitting the data. When you overfit the data, that means that it's going to learn the training examples perfectly. So any picture that you give it, if it has seen it, it will know the answer every single time. But if it hasn't seen it, then since it overfit the data, it is just going to give you random answers. It's not going to be useful because it just learned the specific examples. And then there is underfitting where you just don't have enough parameters and it just doesn't learn anything because it just don't have the enough complexity in the model so that it can actually do something useful with it. And the really evil part is that you can have both at the same time. How can that happen? Well, it can happen because you might have a problem domain where a specific function that you chose, but for part of the problem domain, it is overfitting, like it can perfectly predict cats, but with dogs, it just can't because the number of parameters there is too large, or this architecture of the function is not right for dogs, and so on. So basically, you have this weird situation where you it's not just that you have to increase or decrease the number of parameters, you have to really think about where to increase those parameters and where to decrease. So that's basically the hard part. And then you also have to find the error minimum, which is a whole other problem on its own, because like there is a very famous theorem in mathematics that states that you actually cannot find global minimums. There is always going to be an example that is as bad as you can get. You can basically, if you imagine your minimum searching algorithm, it is going to go through steps to find that minimum, right? And with any algorithm, you can have like this evil magician who is, as we are running the algorithm, this evil magician is putting minimums into the holes of our algorithm where it would never look. And then it can be as bad as you can imagine. So, but we can approximate the minimum. So yeah, there is a lot of math behind these three topics. But for today, I basically just want to focus on finding the right functions, because this is where the most advancements happened in the last 10 years. This is where people were focusing to get this one right. understand what is the right function. And that also kind of solves the minimum finding problem, because if your functions are designed right, then you can actually create functions where finding error minimums is actually easier. So that's it. But a lot of it is just guesswork. Okay. I already talked about this. We don't just add parameters, because then we would have overfitting. Okay. So before I go on to the next section, which is like breaking down the big one magic to smaller ones, are there any questions until this
Yeah,
point?
remind us what the overpredict concept was again.
Yeah, so overfitting is when your model has too many parameters for the amount of data that you have. So basically, you have, I don't know, you have 10,000 handwritten images, like numbers, and you try to learn which number is which. And if your model has too many parameters, it's just going to learn those specific handwritings. But if you get another person and you try to detect those numbers, then it's not going to work, because it overfit on the training data.
So you lose the ability to be general.
Exactly. Exactly.
Right.
And the underfitting is like the opposite, when you just don't have enough complexity in your model. So
And what do you get? A lot of false positives?
find
What happens when you've got,
sorry?
what happens in that case? You get false positives, you get, what
No,
happens when you're
basically you
underfitting?
never get low error rates. So what you would see if you have an underfitting model, what usually you would see is that your error rate doesn't converge. It just stays high.
Other
So,
questions?
so I'm going to check the chat in case there are any questions in the chat. Okay, not yet. Right, then let's move on for now, and let's look at the kinds of magic. And I don't mean black magic and white magic. I mean, like, what steps do we need to create an AI? And I want to look specifically at one example, which is from an image prompt, how do we get to an image? So specifically, if someone asks for a ballerina on a marshmallow motorcycle, how do we get this image? And by the end of this talk, you will have a step-by-step framework on how to do that. And as a byproduct, you will also learn a lot about other kinds of AIs. Okay, so what are the steps here? Well, we have a sentence. So first, what we need to do is we have to turn the words into vectors, because this whole thing only works with vectors, right? The thing that I told you at the beginning is that we need to multiply matrices with vectors. So somehow we need to turn those words into vectors. And we are going to talk about how that is done and some interesting features of those vectors that we will get. Then we need to turn the list of vectors that we got, this sentence, into a meaning. So we have to understand, we have to make the AI understand what that sequence of words means. And then the next thing that we want to do is turn that meaning into an image. And these are the three things that we are going to talk about. And first, and yeah. So basically, I will go through, that's going to be your third step, is just going through all of these things one by one. And for each of them, I would try to give you an intuition of what's happening there. So the first one is turning words into vectors. And one way would be to just assign random vectors to words, or you could also, theoretically, you could also do this. You could just say that I have 10,000 words in my dictionary, and each word is going to get a separate vector with everything zeroed out except for one position. So the nth word would only have one in one position. Problem with that is that you would have really high dimensional vectors. So what people did first was they tried to create vectors that somehow already encode meaning. And there were two interesting experiments here, which one was word2vec and the other is glove. And word2vec was trying to predict the missing word in a sentence. So what they did, they gave the AI sentences that it had to look at, and one word was removed. And this AI had to predict what word was missing. While glove was trying to predict if two words can be in the same sentence. But both of these little AIs came up with so-called embeddings, and they had some really interesting features. One such feature is word arithmetic. So here's the really interesting thing. If you take the word, take the vector for slow, and then, take the vector for slower, subtract slow from it, and then add fast to it. And what you will get is faster. Which is basically what I'm saying is that the difference between the vector for slow and slower is the same as the vector between fast and faster. Same with queen to woman and king to man. So somehow these embeddings like they represent relationships between words. And these are not exact relationships, right? So what you will find if you try to do this yourself, what you will find is that like when you take king, subtract man from it and add woman, what you will find that it's not exactly the same as queen, but it's awfully close to it, okay? And people started to play around with it. And the other thing that they noticed was that the angle between, so if you can imagine two words like coffee and tea, the angle between the two words was basically in relation to how close the two words are in meaning. So coffee and tea are both hot beverages. This angle was really small there, but a ball and a crocodile, those have nothing to do with each other. So that's going to be a large distance. And that's why we define cosine distance, which is basically a measure of similarity between words. So if two words have a low cosine distance, that means that the AI thinks those words are similar, have a similar meaning, while if they have large cosine distance, that means that they are different. Okay. Interesting. I think for me, that was one of the most surprising things. I'm not sure what.
Wait, I'm sorry. Let me
Yep.
make sure that I understand. This is distance in terms of if one word, if the probability of a particular word going in as the missing word in a sentence,
Yes,
that where tea fits, coffee fits, right? Like, can
Yeah.
I get you a cup of, right?
Mhm.
So that's what we mean by closeness, or what do we mean by
Yeah,
closeness?
so basically, there were two different ways of embedding, and both of these embeddings have this property. And one is what you said, like, I can switch the two words for each other. And the other is these two words can appear in the same sentence, or are likely to appear in the same sentence. That's the word2vec model. Glove is what you said, like, no, sorry, word2vec is what you said, and glove is the other one. But the interesting thing is that since these two models, there have been other embeddings. but all of these share this very weird behavior. And it really doesn't matter how you create these embeddings, as long as they are somehow reflecting the meaning of words, you will get these interesting features. Does that make sense?
Yep.
Okay. So now we already have words, but how do we make sentences out of words? What would be your first guess? I'm curious if there are any guesses in the room. How would you try to create a sentence from words?
I assume you'd pick one word and then predict the next.
Okay, but that already think of something much simpler. Like you just have the vectors and you don't want to.
Oh, you have the vectors already and you want to turn it into words. Or you have a.
I have words and I want to somehow
align them to
combine those
make a
words
sentence.
into a meaning of a sentence.
Okay, so you have the words, but not in order.
I could have it in order, but I don't necessarily have to use the order.
But you want all the words to show up in the sentence.
I want to create a vector that is somehow a result of the vectors for the words. So
Okay.
let's say I have a sentence, I am smart. That's 3 words, right? I have 3 vectors, one for each word. And I want to create a vector that represents this I am smart sentence. Add the
You take
vector.
each of the words, turn them into vectors, and then that's your vector.
Yeah.
You just have an array of vectors.
Sorry?
So you just have an array of vectors.
Yeah, you have an array of vectors. And then what we have in the chat as an idea is just add it together. Like add the vectors together. That's one. And that's actually the first thing that people tried. That's called bag of words. And we actually use it for some things. Bag of words is a useful first step. But then there was a next step, which is recurrent neural networks. And I'm going to talk about that in more detail in a second, and why those were useful for some things, but didn't really achieve what we wanted. And then people came up with the transformers, and attention is the thing that enabled transformers to do the things that we do today, right? And then I will also
Sorry to interrupt. I tossed in 2 ideas, and I believe both of them are sides to this problem, apart from being very old-fashioned. So pre-RNNs, for instance.
Sorry, I didn't understand what you were saying at the beginning.
Yeah, so in the chat, I wrote two let's say algorithms.
Okay, engrams and Markov chains of words in order. Wow, okay. Yes, those are also fairly old school stuff. Correct. I didn't want to touch on those because I don't think that, are those still used that much? I'm not sure.
I think engrams are already replaced by neural nets, which technically do engrams under the hood. What researchers found out. Markov chain is super old, so
yeah,
I even believe from 900s the theory is coming from.
Yeah.
So, but if you think of CPUs, these are actually very, very efficient.
Yeah, sure. Anyway, I think that the reason I didn't include them is because RNNs were very intuitive. These are not as intuitive. But let's go on and look at RNNs, because that's an interesting concept. So what people try to do first is the first idea that you already tried adding the vectors together, and then the next idea is we have this neural network. What we could do with it, and the idea was let's create a neural network that takes an input, like it's one word, and it outputs something else, but it also creates an internal state vector that it feeds it into itself. So basically, every time we take a step with this recurrent neural network, we give it two vectors. One is an internal state that starts out as an all zero vector, and the other one is the next word. And we are going to add, like, modify this internal state word by word. And that is what RNNs do. They just eat the sentence word by word and then modify this internal state. And that was an interesting idea. The problem was that, like, it could be used for a few things. Like, for example, it was really useful for sound processing in certain instances, because there the modification that you want to do is fairly local. Like you you have the sound sample that you are modifying, and maybe you want some past data to be around. But I think RNNs were one of the things where it was useful is like transcription. You have an audio and you want to generate text. So for that, it was one of the architectures that worked. But the problem was that because your internal state vector is every time you are overwriting the vector, right? And one of the things that then tended to happen is that the past got erased really fast. So basically, there was no attention span, for better. Like this was really the problem, that there was no attention span of these models, because they just very quickly forgot the past. Okay.
Did you have a sense about how that problem was seen? Like, what did it look
so
like?
for example, when Google was first trying to use RNNs to translate, the way they did it is that you can imagine that your translation machine takes the words one by one. Now, of course, because you have to switch up the order of words, like the same sentence in, say, English and German, the order of the words is very different, right? And especially in German, sometimes your verbs are split in two, and then part of the verb is just transferred to the end of the sentence, which is quite weird. But basically, when you translate, you need to know the whole sentence before you can start translating. Okay? So the way that people try to do translation with this architecture is they gave the model words one by one, and they trained it to return 0 until the first word that was the 0 vector. And that was the signal for the network to start generating the translation. So the idea would have been that as long as I give this network non-zero vectors, it's going to read the sentence and return 0. And once I start returning 0, it will start generating this translation sentence. Problem was that even like it worked for really short sentences, but the minute the sentence got a little longer, it just fell apart.
And we say longer, we mean in terms of counting words or the complexity
Like
of concepts?
word count. Yeah, simply word
Just
count.
word count. Wow.
Yeah. So, but you could do things with it. Like one of the things that I did back in the day is I trained a network like this on all the speeches of the Hungarian Prime Minister, and I made it to predict the next letter. Like it was not word by word; it was letter by letter prediction of what the Hungarian prime minister would say. So it would start writing a sentence, and then it would just try to predict the next, the rest of the text, letter by letter. And what you would get was quite funny, because it would, like, it could return words, like entire words, and those words had, like, the probability distribution was right. And like, you read that sentence and it felt like it was from a speech of the prime minister, because it was using the same kind of words, but it made no sense. Like, the sentences were complete gibberish. But somehow, if you didn't pay attention to what is the sentence itself, you just had this feeling of, oh, this is the prime minister speaking. So they
if you just had the same politicians we have, then you wouldn't have been able to see any difference at all. Now keep going. I'm sorry.
Yeah, I never tried to train it on Trump. It would be an interesting experience. I'm not sure if it would make less sense than Trump, but okay. Let's move on. So then there was this problem of like not being able to have attention span. And basically what the engineers at Google did was they said, you know what, let's not try to put too much effort into this RNN thing. Instead, like, create a network that takes a sentence all together and then transforms it into the translation. And that's where the transformer phrase comes from. This is any network that transforms one data into another data is a transformer. And then the thing that they were trying to do is add attention to it. So what we want to achieve with attention is to allow words from a sentence to refine the meaning of other words in the sentence. So a very simple example. If I tell you that here is a beautiful model, you will think of another model than if I tell you here is a generative model. If I say beautiful model, you're probably going to think of a human. If I say generative model, you're probably going to think of an AI architecture, right? So how do we achieve that? And it is quite genius, actually. So, to give you again, intuition, let's imagine that the words are kind of talking to each other in this example, okay? And the word model is going to say, okay, I want to know what kind of model I am. And then at the same time, generative will shout out, I have relevance to models. So if there are any models around here, I want to talk to them. I want to modify them. And it will also say that models around me are machine learning models. That's kind of the other thing that is trying to message. And what we want to do is put these things together. So we want to make sure that whoever is looking to find out more about themselves will find those things that can refine their meaning and then do this refinement. And the way we are going to do that is using vectors, because we are playing this deep learning game, so we need vectors, right? And we will have these query vectors. Query vectors are basically, so in a attention transformer model, you will have multiple attention heads, and each attention head will be learned, and we don't know exactly what they do. But one example could be an attention head having a query vector that basically represents this question of, like, this message of, I'm looking for someone to tell me what kind of model I am. And then we have this query vector. The key vector is kind of representing what this word has relevance to, while the value vector is representing how that word should be modified. And then the mathematical operations behind this is we are taking the dot product of these two vectors. Dot product is basically if two things are perpendicular to each other, then the dot product is going to be 0. If they are really close to each other, then they will have a large dot product. And basically what happens here is very similar to what we did with the cosine distance between words. So similar query vector and key vector imply that these two things have relevance to each other. If they are not similar, they are perpendicular, that means that they have no relevance to each other. And then we do a so-called softmax. Softmax is a really interesting function, not going to go into it. What you need to know about it is that it's kind of selecting the maximum value, but in a soft way. It's not going to zero out everything. It's just going to make sure that the whole thing adds up to 1. And the largest value is going to be really close to 1. Like it's going to be and that's just so that you can, the reason we are not just doing max is because that's not a smooth function. We cannot do global optimum search on that, but softmax we can use for that. So that's the intuitive thing. It's basically just selecting the pair that like where the relevance is the highest, and then it just takes a weighted sum of the value vectors based on this softmax. So if I really want to simplify it, it takes the two words that have the most relevance to each other and then modifies the first word based on the value vector of the second word. Does that make sense? More or less. So basically, that's the thing that is trying to bring, like, transfer meaning between words. But the thing is that these attentions, like the first layer of our attention is of course going to do this. But as we go down, like you will have multiple attentions below each other, 3 to 4 or whatever. And then as you have multiple of these, the second layer is of course already operating on modified things. So this is not even operating on words. It's already operating on meaning that has been modified. And as I said, this was just kind of an intuitive example.
Go back to where the softmax is being used.
Yeah, so the softmax, yeah, here. So basically, the idea behind the softmax, original, like one example where you would use a softmax is if you are trying to find, like you are creating an AI that looks at the picture and decides what kind of dog it sees, right? And then you basically, for each kind of dog, you will have a probability. And softmax is trying to select the highest probability option. But it's trying to do it in a soft way, like smooth way, so that you can use global optimization algorithms. That's the basic idea. Do you have?
So am I understanding, like I've got this word jack, let's say, which I think is the most ambiguous word in the English language. I think there's like so many, it's a person's name. You can jack up a car. You can, there's all different meanings, right? So I'm given every other word in the sentence. I'm trying to figure out which meaning of jack I'm getting using the softmax function, or how does this work?
Yeah, but that's the same thing you're doing like as a human, right? Like if I say like jack up the car, like you're putting that together because of the other words in the sentence. If I say I don't have a jack, you're putting it together from the other words. And even if I say like I don't have jack, which is a very different meaning than I don't have a jack, right? Like the whole sentence is coming together and you're doing that as a human. Here, the algorithm is doing it. It's modifying the value of Jack by each of the other words in the sentence.
And basically, what we do in the first part is to try and find which word is going to be the most relevant for modifying this word. So for every word, we are looking at the whole sentence, and we are trying to figure out which of the other words in the sentence are going to be relevant in modifying this word. Does that make sense? And that's kind of also the answer to Ken's question, where, yes, when I said first and second, I meant on the slide, not within the sentence. Like you might have a word that is modified by another word that is behind or ahead of it. Like, really doesn't matter. And how does it tell if brown is a kind of dog rather than dog is a kind of brown? That's basically the way it tells is, as I said, this is learned thing. So we can create intuitions. We don't know exactly what is happening. But basically what happens here is Brown is going to say, I can modify dogs. And dog is going to say, I want to know my color, right? And that's why it knows which one is which, because the query vector is going to tell what I want to be modified with, while the key vector is going to tell what I want to modify. Okay, I hope that kind of answered the question. Okay. So, as I said, this is basically just intuition. But the thing that I think is really interesting here is that what happens here is that we completely ditched the just multiply matrices one after the other. And we created this elaborate way of creating the matrices itself that we are multiplying by. And what we try to do here is basically just reducing the number of parameters in a meaningful way that we intuitively understand that if we do this, this is going to have the model learn relevant stuff instead of overfitting on specific sentences. But this is, as I said, a lot of trial and error. And then how do we get from here to ChatGPT? And the answer is that we create a different kind of language, which is the language of the same language, just shifted one word to the left. So what we are going to do is we are just going to add an empty word at the beginning and say a ballerina on a marshmallow. And then we ask the transformer to try and create, like translate this to another language where just every word is just appearing one word sooner. And then we have one extra word at the end. And that's how it works. And so one of the things that is interesting to note here is that the pre-trained transformers are actually predicting stuff that we already know. We already know what the first word is and the second and the third. Like this whole thing, we really don't need to predict because we all know that. We just wanted to predict this last word, but we still go through this whole process. And that's kind of an interesting thing, but it was sort of a hack. This thing was designed to translate, and instead we are using it like this to predict next words. And it works, and surprisingly well. But what's also interesting about this is that if you look at this architecture, like the last word is actually predicted from one single vector at the end of this whole thing. So if you imagine this transformer, it has lots of blocks. You have the attention blocks, and in between you have traditional like just matrix multiplication kind of blocks that we already had before. And in the end, you basically just have these last prediction steps. And the interesting thing is that last, like each word is just predicted from one vector. And this vector has to have all of the meaning, not just the sentence, but all of the text before it is somehow encoded in this one vector, which is weird. And what's even more weird is that these vectors represent meaning so well that if two documents have similar meaning, like they are talking about the same stuff, their cosine distance is going to be close to each other. Not just that, if you ask a question, transform it into this vector, and then you take a document and transform it into a vector. If the document is relevant to the question, the cosine distance between the two is going to be small. And that's where vector database is coming. So vector database is basically
Wait, hold on. Actually, we're going a little too fast. Do you mind?
Yeah, okay.
The thing you were saying, that the word is predicted by a single vector. Can you, what was the point you were making there? And can you slow that down and explain?
Yeah, so the point I'm trying to make is that this transformer, the way it looks like is that before you get a word, the last step is you have a vector that is representing the sentence or the text before that word, the whole text before that word. And then this last step is actually just one last traditional matrix multiplication and then the softmax, which is
Wait, I'm
going
sorry.
to
Are you
like
saying when you say
most
all the
probable.
text before that word, you mean all the text could be paragraphs and paragraphs, or just the sentence before, or
The entire context length? It basically that's why context length is a big thing with LLMs, because if you look at this, like the input to this transformer is a fixed length, and you can fill it up with empty like zeros, which means like you are not inputting anything. But in the end, you have a fixed size to this transformer network. And if this fixed size is, if the whole text fits into it, that means that the transformer can work with the entire context. But once your text gets longer than the size of the transformer's input, then it's just going to cut off anything before it.
so you were just, so then say it slower again. The entire context to what point is what, say this sentence again so I can.
Okay, so well, when we talk about LLMs, there is this very important metric that they always mention. What is the context size of that LLM? Right, and this is the thing that they are trying to jack up from month to month. And the context size is how many tokens or words you can feed into a transformer. So if I don't know the answer to that question, Ken, sorry. But basically, if you think like, let me give you an example. Let's say your transformer has a context length of 10. That would mean that you can give it 10 words. But that's the maximum amount of words that you can give it. And then it's going to predict one more word. And then you can only use 10 words. That would be a context length of 10. Nowadays, the context size of these LLMs is about like you could fit the entire Harry Potter series into it. That's the size of these models these days. But the thing is that like the context length is how many words you can feed in on the top. And in the
Wait,
bottom,
does that mean that I could feed a query in the size of Harry Potter's the Harry Potter series?
yeah, you could give ChatGPT that amount of data to then generate.
Oh my God, I assumed. Okay, great to know.
Yeah, it's weird, but you can do that. But the thing is that, and that's kind of why it's so expensive to run these models, because like they are huge, right? And but the point is that at the bottom, for each word, it's going to have a last vector that we calculated, and then it's going to make a last calculation with that vector and take the most probable word based on that. And this last vector, like after every word, for every word, this vector represents the entire text before it. That's what I was saying. Does that make sense?
I'll probably come up with more questions. Yeah, keep going.
Okay. And then when you take this vector, it has this severe interesting property that it actually has a small cosine distance if the meaning of the two sentences are, or two texts are similar or have relevance to each other. It's just a fun fact. So at this point, we have meaning. And then I just want to briefly talk about, because we are already talking for a long time. It's over an hour already. So let's just briefly talk about how this meaning becomes image. But before we talk about that, I just want to touch very quickly on what caused this huge drop here, because it's a very interesting idea. And I think it's worth talking about. And that is convolution. So imagine that you are trying to detect what number is written with handwriting. And what like the traditional way of doing this would be to treat each pixel separately and train the whole network. Like the way you treat this part of the image is going to be very different from the way you treat this other part of the image. Like I should probably show it here, right? But the idea is with convolutions is that we are going to do something slightly different. So imagine taking a 3x3 part of this image. It's represented by numbers, right? This is how bright the pixel is. And then a convolution is this. You take a convolution matrix. This is the part that we are trying to learn with machine learning. And what you're going to do is going to take the numbers that have the same position, so in this case 3 and 0, and you multiply them together and then write it into the box in the result, right? And then you do that again for 3 and -1 and so on, right? And then you get this matrix of products, and then you just add this whole thing together. And that's going to be the result of your convolution for that one pixel that is the middle of this 3x3. So basically what you do is for each pixel, you take the 3x3 around it and you do this convolution operation on it. And it is interesting for two reasons. One is that this allows us to treat the entire image uniformly, because the convolution matrix is something that we are going to learn once for the entire image and not separately for each pixel. The other thing that is the reason it is interesting, because convolutions can do really interesting stuff. So this is the trivial convolution where you just have 1 in one position and 0 everywhere else. Well, what if you do something like this? That will create a blur. This is the blur effect, this simple Gaussian blur. Or you could do something like this where black represents -1, white is +1, gray is 0. And there it becomes really interesting because this actually shows edges, right? So this is edge detection. And you can do a whole host of interesting stuff with convolutions, like unsharp mask. If you open up Photoshop, like half of the filters you have are actually convolutions. Unsharp mask, blur, edge detection, this light effect, emboss. These are all examples of convolutions. And what people did was they took the image and then learned these, like they put convolution after convolution. So you have one image, you generate a couple of convolutions from it, and then you take those convolutions and convolve them further and further. And what happened was these little convolution matrices learn features. So the first level would be like edges, like the direction of an edge. But then the second level would learn something more complex, like irises of eyes and like edges of mouth and all those kinds of tiny details. And then even higher level features would come up in layers below. And then you would use another more traditional network to decide then what is it that you see. And this convolution idea was the thing that started this whole revolution. And then once we had that, then someone had this idea of generative adversarial networks. And this is something really interesting. I really like the architecture. It was surprisingly useful, but it was really a pain to train, and it really didn't get where we expected it to get. But the way it worked is that you would have this discriminator network, and the discriminator network's job was to decide if it's seeing a real image or an AI-generated image. And then you would have a network that took a random input and tried to use that random input to create an image. And then what you would do is simultaneously try to train this generator to fool the discriminator, but also train the discriminator to try and make distinction between real images and fake ones. So this is, if you saw the movie Catch Me If You Can, like the guy who creates a fake money, this is exactly that, right? The discriminator getting better at recognizing fakes, but the generator also getting better at faking. And this architecture could get us.
So can you walk through that diagram?
Yeah. So for example, so basically what you have is you have real images. This is what you feed the network as data. And you want to create images that look like this. And what you do is take a couple of examples, give it to the discriminator, and you also have this other network that takes just a random vector and then turns that into an image, which at the beginning will be complete nonsense, right? And then you sample from that, and then you train this discriminator to be able to tell the fakes from the real images. And then you stop doing that, and then you train the generator by making it so that the discriminator is fixed, and you try to train it so that it gets better at fooling the discriminator. It tries to make better fakes. And once the fakes are good enough, then you switch back to this other mode where you're training the discriminator on trying to make a distinction between real and fake. Does that make sense?
I'm going to need to ask you more questions. Yeah.
Okay. Does it make sense to anyone else? Okay. I see Llewellyn nodding. Okay, then let's move on. So basically, this is what it gets you. You get these images that kind of look like this. This was trained on pictures of bedrooms. And like your first impression is that you see bedrooms, but if you look really closely, then one, these images are really, really tiny. Two, they are really not bedrooms. Like they are horrible, crappy images. But there was something interesting with these. So the interesting thing was they also trained it on faces, and these are the kind of faces that guns could generate. And here's the thing: if you take the vectors, like if you remember, we had this random input here, and this random input is a vector, and we take the vectors that generate male faces with glasses. And then we take the vectors that generate just male faces. And we take vectors that generate female faces. And then we do vector arithmetic on it. So we subtract the man from man with glasses and add woman. Then what we get is a woman with glasses. Which is like mind-blowing, right? You can do arithmetic on images.
Oh, that is crazy.
That is crazy. And then someone had the idea, okay, we can already create meaning from words. So what if we did something different? We don't just give a random vector to the generator, but along that random vector, we also give meaning. And when we train the discriminator, we also give it the meaning for both the real images and the fake images. And what happens is this: you can create a network that takes a prompt and then creates an image. And now these look really funny, right? But keep in mind that this is like 5 years ago. Like Midjourney was nowhere, and we could already do things like this. The images were tiny, but you could already create images based on prompts. And like that was how GANs work. But the problem was that like they were really hard to train because they were unstable. Really, really unstable. It was, if you trained the discriminator too much, after a while, if you didn't switch early enough between the two modes, you got this mode collapse where one of the, either the discriminator or the generator got too good, so the other one couldn't catch up with it. And then there was this other thing, high like resolution upscaling. Yeah, that's the word. So upscaling images. And that worked really well because that was just, you just took an image and you trained it to try and like we basically upscaled it with just repeating the pixels. And then there were these networks that you could use to remove the noise that was generated by the upscaling. And it worked fairly good. This by the way, this upscale is like 5 or 6 years old. I didn't do it now. And then someone asked the question that, like, what if we just we didn't have noise from upscaling, but we just have noise in an image, like random white noise. Can we remove that? And how much of it can we remove? And the odd thing is that you can remove all the noise. And that is stable diffusion. And the thing is that if you try to remove all the noise at once, that doesn't work. But if you add just a bit of noise to an image that is, it doesn't matter how noisy it has some noise, and you just add a bit of noise and you train the AI to always try to just remove that amount, that small amount of noise, then you can get to this algorithm where you start from noise and you incrementally remove the noise until you get an image. And that is how stable diffusion works, which is quite interesting. And that kind of also highlights one of the conclusions that I want to make. And I will just walk through the conclusions for a second, and then we can keep on discussing if you have any more questions. Yeah, so first conclusion. I kind of hope that after this talk, you can appreciate this meme a bit more. That's one that I really like, because in the end, really, if you think about, like, one of the things that we do here is really just lots of if-else statements, like matrix multiplications, and then just removing anything that's negative. So that's the story behind this meme. The other conclusion is, like, be aware of like, this is Clever Hans. Clever Hans was a horse that could do arithmetics. And it was like all this wonderful thing, and people try to find out how it works. But there was an interesting thing. When Hans's owner was around, Hans could do arithmetic. When he wasn't around, it couldn't. And the thing is that what happened is Hans learned that it should stop stomping with their feet when their owner starts to smile. Because just the smiling was the thing that indicated to the horse that, okay, I got to the right number of stumps. And that's kind of the thing that I want to highlight here, is that be aware that you don't know what the AI learned. That's what I'm trying to say. It might have learned something that you don't expect it to learn, and might be making judgment on something that you don't expect. One example was, like, they trained an AI to recognize what kind of fish is on a boat. Problem was that the boats that they were, like, the images of the boats that they were training on were from different parts of the ocean. So basically the AI learned which boat it sees and not what fish it sees. And that's kind of a tricky thing there. So generative AI is awesome. It's not magic, and has some limitations, mostly that it can only generate things that fall in between the data that it already has. And creativity is mostly just limited to very simple metaphors, and mostly just being able to interpolate between the things that it has already seen. And then what's next? Like, of course, none of us know. I don't think that the current architectures are going to be able to go much further, but this is just a guess. Albeit a guess informed by talking to people who work with these kinds of models. But I also kind of have the hunch that the next step is going to be something like what happened to GANs, like generative adversarial networks, to stable diffusion, of, like, trying to make things more iterative. Because right now, LLMs try to do the whole work at once. And I think what might be the next step, and this is, as I said, just a guess, is that it will try to take a more incremental approach. That's it. Are there any questions?
I couldn't hear that last thought. A more incremental, you said?
Yeah. So basically just not trying to do the whole work at once, but, like, try to build up to, like, this is something that people try to do with there is this prompt engineering term, chain of thought prompting, right? It's tell the AI to think step by step and try to reason its way through the process. I think that's a good first step in that direction, but I somehow have the feeling that there is there is probably a way to stabilize these processes better if it's not just the prompting. But that's just a hunch, really just a hunch. Just out of curiosity in the room, like how much of this did you get? Like, was it more like 10% or 50 or 80? How easy was it to follow? Because I feel like it's really a fire hose of information, but some 70%. That's good. Good. Okay. That's okay. 40? Okay. All right. So there is quite a bit of variability there, but I kind of hope that it was still useful in some way. Okay. Any
So back
questions?
to the initial question that I asked. So now knowing this, what kinds of things, like for example, I've never been able to get ChatGPT to generate a good joke, one that would actually cause me to chuckle. Given if I understood 100% of this talk, would I be better at figuring out why that might be the case?
Okay, so I don't think anyone really knows the answer to that, but I think that I have a few guesses to why that is. One is maybe it just didn't see enough jokes. The other option is like creating a joke is like multiple steps, right? I'm not sure if you have read, there is a really good book on how to create jokes, and it's called Hitting Your Funny Bone. And it takes you through the steps of creating a good joke. And I think that it kind of relies on like think a lot backwards. Like, I want to have this punchline. How do I set it up? Right. And maybe that's the reason, because it takes a lot of like one of the things that William was talking about last week is that you can't get ChatGPT to think about code that has like multiple layers in direction or something like that. And I think that's a similar thing where it's just that you don't have enough attention layers to create that kind of connections. That's the other option.
When I watch videos that are assessing AI, one of the questions that like AI is really, really bad at is how many words will your response have? Like it just none of the AIs can give you an answer that has the right number.
How many words of?
How many words will your response have?
Yeah.
Right? And so there's something about like when you were talking about taking a joke and starting at the back and like I can very easily take like 5 words has this response, right? Like I can construct backwards, but AI can't do that, right? And so I think that might be related to the jokes.
So I might suggest there's somebody, I think it was Minsky, but that had said that jokes are the way that we socialize our understanding at the fringe of the questions and the surprises at the fringe of our understanding. And that's the reason why we outgrow them as well, is that that's a moving target. So since this doesn't have any meta understanding of itself, it might be uniquely blind to that particular area, and that might not be the best thing to be asking it about. That might be sort of one thing. And it goes to another comment actually that I was wanting to make when you were doing the thing where you're layering on the different attributes and you're saying that there was some sort of like basic feature recognition and then some composed feature recognition. There was like a matrix of that sort of thing. This seems to be sort of domain independent. Is it building up sort of from pure mathematics or something, and you're pouring in data and then doing these recognitions in a kind of abstracted kind of way. And it's not clear, in my mind at least, that nature did it that way. That it may have, for example, because of survival needs or something like that, found that certain things were actually so important that there are very special biorecognizers for certain things that are not in mathematical parity with other things that might seem equivalently important. And so as you build up from them, you get a certain set of things that are sort of uniquely useful to the world we live in, and sometimes really bad for the world we live in if it turns out that there's something new coming along that we have no recognizer for, climate change or something. And so that might be something where when you're talking about the dynamic AI or the incremental AI that's coming along, like if you were to teach computers, you start from like waveforms and you say, okay, like if this waveform is very high, we're going to call it 1 bit, and it's below, it's going to call it 0 bit. And then we sort of build up from that through various abstractions about gates and whatnot up to the things that we actually talk about. You could describe those things in terms of like, wow, my program broke because a waveform was wrong. But that's a very bad level of abstraction. And maybe the complexities that we seek to reach rely on having chosen that stack of abstractions correctly and not just wasted the expressional power of saying we could have chosen any abstraction at any layer or something. That might not get us to where we need to go. Does that make any sense in the context of this?
Yeah, there are actually a lot of things that I want to reflect on now. Reflect on this last one. Yes, probably. Like, I think, well, like even with the current AIs, when you phrase your questions with the right level of abstraction, it can give you a much better answer, right? That is why someone who is well-versed in programming will get much better results from ChatGPT generating code than someone who doesn't know how to code, right? Because you can hit the right level of abstraction for GPT to generate the right answers. But yes, I mean, probably that's also true at the architectural level. Like that's what you meant, right?
Yeah, I was thinking that maybe just that there would be specialized recognizers that might be a thing that comes along rather than general purpose ones or something.
That's also possible. And one thing that's really interesting is you mentioned that like nature probably learned these things differently. And what's interesting is that we have optical illusions, right? Humans are susceptible to optical illusions. What's interesting is that AIs are also have their own optical illusions, but it's different illusions. You can generate images that are specifically designed to fool the eyes of computers, but don't fool the eyes of humans. And also the way around, where you can have optical illusions that are optical illusions for us, but not for the AI. And this is actually really dangerous because you can generate for every specific image recognition algorithm, and this is important that it has to be specifically for an image recognition algorithm, you can design an image that if you put anywhere, it's going to recognize it as a banana, say. And that's a problem because if you have an AI driving a car, and you can create an image that you just stick on the wall, and then when the car drives that way, then it suddenly starts seeing everything as a banana because it saw that image. That would be bad, right? Because it can run over bananas, but not humans. And that's one of the things that is really interesting, that you can create these kinds of illusions.
I mean, there's the same thing though for humans, right? Like you can put optical illusions on the road that cause just as much trouble for humans, right? And we don't because we want to drive.
Yeah, true.
But it suggests a way to create a symbiosis too, a way to keep people having jobs is to understand that like the additive power of being able to do two different mechanisms for something, like to be able to drive and have it do the lane crossing detection is probably better than saying, well, it knows better than you about how to cross lanes. Like the two of you together know better, but not necessarily one replacing the other, because our intuitions are wrong. There are two things we're obsessed with the fact that we know things, but we have less understanding of where that things we know fall off a cliff, and we don't know things, and we know how people degrade. So if you hire a person and you assign them a task, you know both what they'll do and where they're likely to fail. But we don't yet know where computers will fail. We don't know the sort of geometry.
I feel you might be overestimating how much we understand humans.
That might be. I mean,
Like
maybe,
quite a big bit.
but we build in safeguards for statistically what we're used to people failing at. And we don't know statistically yet what we're used to computers failing at. We just know what
100,000 people die in a car a year in the United States. I think safeguards might be a strong word.
might be. I don't know. Yeah. But it gives you a roadmap for how to think about how industry or useful symbiosis might be collaborative.
I mean, so I think there's the part that symbiosis is real, and definitely at the moment it's very real, right? Like we're nowhere near AI taking over the world. But I think a lot of the times we have very double standards when it comes to what we find acceptable for robots or machinery or programs and people. I mean, we even have like weird double standards with programs and knives, right? Like I have a kitchen knife and I can do horrible things with that knife and nobody blames the knife, right? But if I do something bad with a program, people get upset at the program.
Mm. Yeah. Yeah.
There's a talk that from an Entropic guy at Strange Loop, and he shows the images. So for image detection, you can reverse it, and you can create the image that hits the highest yes for the image. And so like on all the slides, he has like, if he's talking about like right facing dog, he'll have like the AI, this is the canonical right facing dog. And none of the images look anything like what it's like if Dolly, like if you went to the Salvador Dali and said, draw me a right facing dog, is like the essence of the dog, but it's not looking like
but
a dog.
There is this Deep Dream, or what was the name of it? Google Deep Dream. What they did there is like take an image, make the AI recognize the image, and then we told the AI, okay, this is how you recognize it. Make it change the image so that it's even more fitting what you think it is. Like amplify the things that cause you to believe that this is what you see. And we just give you an example of that. The dream images. So yeah, here is one example of what you would get if you do that. Share screen. This one. So these are the kinds of images that you can. And what's interesting is that, like, I showed you that there are multiple different levels of recognition. So depending on...
I'm sorry, these are the kinds of images you get if you do what?
So you take an image, right? This is, for example, this is the Mona Lisa. And then what you tell the AI is you have those layers of recognition, like that what I showed you, where the first layer just detects edges, the second layer more complex things, and so on. And then you take one of these layers and you tell the AI that this is the thing that you got to. Like these are the values that got high, and these are the values that ended up being low. And I want you to amplify this. I want you to change the images in a way that where you see a faint hint of an eye, you make it look more like an eye. If you see a hint of a nose,
IFI the whole image. Like
it basically dogifies the whole image, because it saw a lot of dogs, and it tends to like in general, deep dreams tend to have a lot of animal faces in them. But it really depends on what layer you amplify. If you amplify lower level features, you will have slight different, but like this, like this is crazy, right? This is just the Starry Night. And what's really interesting that like down here it even added some cars and stuff like that.
But people do this too, right? When they look at clouds, they see
Yeah.
faces and stuff. And so if you were just to point
Wait,
this at
they're not
clouds,
actually
you
in
would probably
there?
do what people do. Right. I mean, it's
Or
kind of
bad
like the
pieces of math.
So yeah, this is exactly what you mentioned here. It's like this is the image of a cloud, and then you create a deep dream that would look like this. Right. And as I said, it depends on like here, I think they choose a lower level feature layer, and that's why we don't have faces in it.
Mhm.
But if you chose a layer that is closer to the prediction part, then you would have more faces.
Hmm.
Yeah. And it like you can properly have nightmares after looking at images like this.
Or religious symbols.
Yeah. Any other questions?
Thank you.
Thank you. It was a long talk.
Thank you very much. We hope you will come back. Actually, everybody, we are I want everybody to feel invited to come up with topics for talks. Typically we do them at this time of day, but on Wednesdays. But that's not the only possibility. And I will stick into the chat on my Calendly link so that you can pick a time to talk to me about when you might want to do that. And let's see what else. Oh yeah, I should quickly talk about what's coming up. That would be cool.
And the time change.
Pardon me?
The time change on the one you got wrong.
Oh yes. Yes, remind me. Yes. But which week is that?
I don't remember which one it was. There was one that was scheduled for like the middle of the night. If you have one scheduled for the middle of the night, you might look again and see that it's got the right time.
Yeah.
It was like 10 o'clock to midnight on Eastern time, or 7 to 9 Pacific. But it's
right.
early. It's really earlier than that. It's around noon.
It's at the same time as all the others. So let's see here. What do we have coming up? It is my events, right? So the next one is designing and building a conversational AI with Scott Swan, and that'll be on the 29th. And then getting good with GitHub Copilot on June 5th at 3:30 in the afternoon, and harnessing conversational AI next gen dynamic content generation with Jasper Bell. And that's coming up on June 12th. So be in touch with me about your topics, and let's get more weeks booked. Thanks so much. Thank you, Ivett.